homework will be out on so next week Monday, and then hopefully you've seen the grades for the quiz and for so for quiz 3 and also homework 4 have been, or homework 3 had been posted. So the grades there were an average a bit lower than they had been earlier in the class. At least wait till you get this stuff up and running. Oh, it's running. Great. So I was thinking about what to do about that. So overall, the grades in the class aren't like super low. Kind of a good percentage of the class are still getting A's and B's in the class. So I'm too worried about overall. But if you guys did not understand the material in quiz 3, I'd like to I'd be willing to assign like some bonus questions on homework 5 where you could get extra points for doing more work so like on those same topics. But then on homework 3, I had this bonus question asking you to try and do gradient descent on this hard function, and it seemed like no one in the class went like above and beyond and earned any extra points, right? So if people are going to do if I give bonus questions and people are actually going to do them, then so then I can give them. Be willing to award up to like 20 extra points, for instance. So the other one, it was only 5. I'd be willing to award maybe up to 20. But if you're not going to do them, I'm not as interested in creating these extra points. So the other thing I did, I created a practice quiz 3, and the feedback icon that was actually so like kind of negative because there wasn't a lot of overlap between the questions on the practice and the actual quiz, which was kind of on purpose because I don't want to give you questions and then ask the same questions on the quiz. So if I make another practice quiz 4, probably will be similar, right? I'm not going to ask the same questions on the practice and also on the actual quiz. There is a practice exam as well, which I haven't looked at in a while, but basically has versions of questions which will roughly be the same as the sort of thing I'll ask on the quiz. Would a practice quiz 4 be more helpful, or would bonus questions on homework 5 be more helpful? So the bonus questions, you think? Yeah. So they might be like a little bit more difficult than a regular homework question, but not like so much more difficult. I don't want to ask the same sort of questions. I'll make you kind of. But the goal is, I'm okay with the grade distribution currently in the class. If it's higher, actually, some of the lecturing faculty will kind of be mad at me for having grades too high on average, which I think this is kind of the electives, this maybe, I don't know if this is an easy or hard elective, but I'm happy, I'm more interested in you guys learning the material than making sure the grades are the right way. So, okay, so then I'll plan to add some bonus questions in there, but I probably won't do a practice quiz number 5. That seems reasonable. Okay, good.
Yeah. Question about the homework. Just make sure I understand something real quick. It's like on each step of your run, print out a single line. The value of a function f, estimating the sum of squared errors.
Yeah.
Is that just the sum of squared errors, or what is f supposed to be exactly?
Oh, it is your, yeah, so f should be the sum of squared errors.
Right.
Yeah.
So, I just got confused about the word like.
Oh, estimating in there. Yeah. No, f of that model should be the sum of squared errors. Yeah.
Great. Thank you.
Yeah. Good. Yeah, and it's okay if you print out long strings of things. Just kind of keep in mind the T's will scroll through these when they're grading them. If it's pages and pages and pages of stuff, it might mean that you've got like the learning rate too small, or you're starting from some point, so which is completely ridiculous. But you know, if it ends up being 1 or 2 pages of stuff, that's pretty easy to scroll through. But this is also a way where we can look at what you did and kind of check to make sure it's working right without seeing the code. And in general, this is what you're going to have to do if you're using these. You're going to hopefully look at your own code and think that's correct, but you won't know it's correct. You'll only be able to kind of tell by looking at these sort of printouts typically. So this is kind of the right, you're often doing this in practice anyways. So, yeah.
I can't remember the exact wording, but it's like, do this as long as you want, essentially. Does that just mean like you can just assign it a specific number of iterations? Or do we have to use like T or tau, basically kind of what I just ran it for a certain number of iterations.
Yeah, well, if you run it for a certain number of iterations and it's converged when you're done, it's fine.
Right.
If you did it and you set the learning rate too small and you're pretty far from converging, then that's not fine, right? So it's okay to say, well, I'm going to set the number of iterations and look at the printout and see if it looks like it converges.
Okay.
And if it doesn't, maybe I go back and adjust the learning rate. This is not necessarily that far from how you might do this in practice, right? It might be better to write a converged condition, although that's going to be actually slower because you have to do this check every time. Right, so there's kind of a trade-off between these two, and there's not one that's necessarily right or wrong. Yeah.
I was wondering, especially for like function 2 in the third problem, I was having a hard time like visualizing it, and so like looking at the contour plots, I was like, what direction should I be moving in? And I kind of got lost in that space. Do you have any suggestion?
Is this function 2? Oh, on homework 3.
Yeah, on homework 3. Yeah.
Okay.
Function 2. Do you have any suggestions like visualization tools just to like ground yourself if the contour plots aren't really doing it for you?
Yeah, so function 2 was one of the reasons, there's a couple reasons I have this function in there. One is you can visualize pretty well with the contour plot visualization I showed you. You have to play with the parameters yourself though, right? So I didn't want you just to run it and not think about it. I want you to have to play with the parameters to get something that looked right. There are, what do I use? I am like a little bit of a Luddite, so I don't want to maybe the T's of other suggestions for visualizing complex functions in 2D. Like there's a program called Grapher on the Apple that I would try and use. There's some things in Python and MATLAB I've used that will try and automatically show you functions in 3D and do this on. But it's tough when it's really kind of skewed like this or have these really sharp drops. And in general, you're not going to have 2D functions, so you're not necessarily going to be able to plot them. So you're going to have to just use like the printout of the string of values you're getting to try and assess whether you're doing something. Yeah. So you can use those tools that I gave you, but you have to play with kind of the domain, both x and y, and in the z, kind of what the level sets you choose. And so I did it when I was creating homework, and it took me like 15 minutes to find the right parameter settings. It wasn't that straightforward, but even I was able to figure it out. I don't know if it gives you a lot of confidence in me, but yeah. So okay. So any questions? Good. So we were talking about clustering. Okay, and so last Wednesday we talked about the k-means. So formulation, and so this is a formulation. K-means is a formulation, not an algorithm. This is to find takes in a set x in say Rd, and a value k, and then the output is going to be a set. S is going to be S1, S2, up to Sk. These are also in RD, and your goal is to minimize this cost function xs, which is going to be the Euclidean distance summed over all the data points of x mapping onto the closest center squared. So the sum of the squared distances. Remember, this function mapped onto the closest center, and it kind of captured kind of which points are in which clusters. Okay. And to solve this, we talked about an algorithm called Lloyd's algorithm, and this had this simple iteration. So let's say I'll initialize with S as a subset of X, and then I'll repeat two steps. One, let me make sure I get this right. Yeah, so the first step is for all x and x, I want to assign essentially x to phi of s x. So I'm going to assign it onto the closest center, and then 2 for all Sj in S. I want to set Sj equals the average of each Xj, which is the set of points such that X equals phi of j of X. All right, so it's just these two steps. I repeat by actually physically calculating this function to assign everything to the closest center, and then for each center, taking the average of all these points. Okay, so this is the simple algorithm that we talked about last time.
Sorry, the k right there, that's just in the very top, the k means formulation? That's
Yes.
just the number of center points?
The number of centers.
Oh, okay.
Yeah, good. So this is the number of the centers. Okay. Okay, and this is given on the formulation. Okay, and this formulation is super popular for basically two main reasons. The first reason is that there is this simple algorithm, right? This simple algorithm works mainly because we can do this average step, and this average is the optimal step to take if we're going to, if we want to minimize this objective. Given a fixed assignment of points onto a center, then the average is the optimal step to take, right? Okay, so sorry if I wrote this too small. I wrote it up bigger and cleaner on last week, and it's in the notes pretty clearly. But kind of just so we can point at and review, it's up here. And so this averaging step makes this easy to solve. Okay, at least as a heuristic. Remember, this was not guaranteed to necessarily converge to the right solution. But in general, it usually works, and especially if you re-randomize this step. I randomly select a subset of centers, and if I randomly restart, then for most reasonable things where you actually want to find k clusters, then on some random initialization, this will converge to the right answer. I can just run it a bunch of times and find the one with the smallest cost function for each initialization, and that kind of, that's the answer I return. Okay, there are other more complex and formal ways to initialize this, and the data mining class in the spring, or there's a clustering class, which also talked about some versions of this as Okay, so the other reason why this formulation is kind of useful is if you look at this cost function, the sum of the squared distances. If remember from like the beginning of the semester, this looks like log of normal error. Okay, so this looks like the log of the normal of the error cost function, where I said let's assume that there's some model and everything has normal or Gaussian noise, and I want to find a representative of it that minimizes the product of the probabilities. If I assume they're all independent, then that's the joint probability. If I take the log of that, it turns out that maximizing the likelihood is equivalent to minimizing the negative log likelihood, and the negative log likelihood looked like a sum of squared distances onto a model. Okay? And this showed up, then it showed up in linear regression, it showed up in dimensionality reduction, and it's showing up here. Okay, so this, it kind of comes back to this normal error model that we started with. And so today, the main part of the lecture is going to be saying, well, what happens if we actually want to try and take this input data and fit Gaussians onto it? Fit the best fitting Gaussian models onto this data. And this is called the Mixture of Gaussians problem. And that's what we'll talk about mainly today. It turns out that the most common algorithm, again, for this is just an extension of Lloyd's algorithm. Okay, so it's not exactly Lloyd's algorithm. You want to add a few more embellishments onto it. But this is the starting point. Again, there are other algorithms for that problem with various other sorts of guarantees on them, and they usually involve a combination of PCA and some kind of fancier versions of this formulation if you want to prove something. But in practice, people use some version of Lloyd's algorithm, which is what we'll talk about in the lecture today. Okay, but there are two other points I wanted to go over before we start on that. One will be directly related, but first I want to talk about this choice here of K, right? What value of K? Okay, so I told you that this is the given to an input, okay? In the real world, it may not be given to you an input, okay? In this problem, to keep stuff simpler, it is, but in the real world, you're just saying, here's some data, can you cluster it, right? Yeah.
Sorry, so K is also the number. Is K the number of sites?
The number of sites, yeah, that's right. So how many centers to pick? And it's actually the same issue with doing dimensionality reduction. Okay, if I want to go down to maybe 2D or 3D for visualization, well then I kind of know what K should be. It's 2 or it's 3. But in general, if I want to just reduce noise to find a simpler model, and I want to go down to like 8 dimensions, well then, how do I choose 8? K equals 8, right? How do I choose that? And this problem does not so much arise as kind of a nebulous issue in regression or in classification. This is an issue large, because there we can do cross-validation, okay? Because this is an issue in these unsupervised setting. So I'm not given labels, I'm just given data, and I just want to find underlying structure of the data. Right, so this would be like in clustering and in PCA, this is an issue. Okay, and there's no, the challenge is there's actually no really good answer for this, but I'm going to give you kind of a good rule of thumb to try and go by. Okay, what's going to happen is you're going to have some value of K, which I can plot, and I'm going to have some cost function for x of S k, or something like this. This cost function will, I'm going to solve, I'll fix a k and I'll solve for something, and I'm going to get a cost. And what's going to happen is that the cost function will go like this. It's going to always decrease. This is going to happen with PCA and with clustering. As I get a bigger model, my cost function is going to go down. For a fixed k, right, for one fixed k, I know how to solve it. Right? If I pick, you know, k equals 5, then I have an algorithm I know how to solve. Right? And then this one, I can't do, you know, this is as good as I can do for that value of k. But if I increase k, the cost is just going to go down. And it doesn't necessarily mean that it's better as it gets further down. It means I'm capturing more and more, I guess, esoteric parts of the model, or parts that might be kind of really just noise, where some of them are part of the real core structural part, and some of them are just, I'm just capturing noise. And how do I know the difference? Okay, and so the kind of, the rule of thumb is kind of what's called like the elbow technique. Is these plots usually look like this, and you can think of these, you know, as, you know, someone's hand, and they're reaching down like this, and their elbow is somewhere, and you want to pick the value of k at the elbow. Okay, where exactly is the elbow here? It doesn't really matter, right? What's the best? Should I pick it here or here? You know, it's kind of, it shouldn't matter too much, right? It matters if you care about 2 or 3 dimensions for visualization, but otherwise you're just trying to come up with a simpler model. The idea is I'm really decreasing the amount of variation in the data. I capture a lot by increasing k, but once it starts to leveling out, I'm not really capturing that much more. And so when it starts to level out, I kind of want to stop increasing k because I'm not really gaining a lot of explanation by increasing the complexity of the model. And so that's about where I would stop. Yeah.
So it's not really like worth our time to take the second derivative of that function and like find where it's the highest and where it's the lowest.
You know, it depends on how long it takes you to do that. It's going to be, I mean, the issue is it's going to be monotonically going down. It's not necessarily going to look like a nice smooth curve, though. Like the second derivative, you have to define this kind of as a discrete derivative. And, you know, you could do that if you're looking at really big values, but that's going to be noisy as well. It's best, I would plot it and look at it and kind of use that as a guide. Okay, so that's not necessarily very satisfying, but this is, you know, in most cases, about as good as you can do. Okay, next I want to talk about soft clustering. And so this is actually something that we'll use in the mixture of Gaussians. The right way of doing mixture of Gaussians involves soft clustering. And the idea here is that in hard clustering, this formulation, each point was assigned to exactly one cluster. In here, I say each x is assigned some weight some weight j onto cluster j. And it's going to have the properties so that the sum over these is going to be equal to 1. Okay, so the sum of the weights will be 1. So if I'm doing the hard clustering, it's going to be 1 for one of the clusters and 0 for everything else. Okay, but in the soft clustering, I can say, well, I'm not sure where this point is assigned, so maybe it's kind of 60% in one, 40% in the other. right? So an example might be like, okay, so I've got two clusters, S1, S2, okay, and so now these 3 points, or these 2 points are assigned to cluster 1, 3 and 4 are assigned to cluster 2, but this one, point number 5, I'm not sure which cluster to assign it to. Right? So it's kind of in the middle between both of them. And so if I think about how I would implement a version of, let's say, Lloyd's algorithm, I would probably have an array for x, where it's going to so I'm going to have an index for each of the vectors, and I'm going to assign these onto 1, these onto cluster 2. So points 1 and 2 are in cluster 1, 3 and 4 are in cluster 2, and I just store this index, and then I can just update this index as I'm iterating through. Okay, but for cluster 5, maybe I assign it to point 1 here. Okay. Now for the soft clustering formulation instead, I want to store some distribution. And now for x, again, I'm going to have this array, but it's going to be a k-dimensional vector for each of the points. And so maybe now I do 1, 0, 1, 0, 0, 1, 0, 1, so this is cluster 1, cluster 2, and this one might be 0.6, 0.4. So I'm storing in here some weight. Okay, and then every time I update the centers, I'm going to update these weights. Okay, there are other clustering formulations where the weighting is done in a way that's different, but this is kind of, I think, the kind of a computer scientist point of view of how to do it for this kind of family of algorithms. Okay, in the Mixture of Gaussians algorithm, we're going to actually assign this larger weights, and then we're going to normalize the vectors so they all sum up to 1. That'll be L1 normalization, not an L2 normalization. I'll think of these as vectors, and I'll L1 normalize them, so the sum of the weights is going to be 1. Okay, so this is soft clustering, and this kind of allows me some nuance for points that are on the boundary. And this is maybe a little bit more stable than points on the edge. Okay. Okay, so does this make sense? Yeah.
Just to make sure I understood the last part. So how you would get that is you would just like take the distances to all the points, and then you're normalizing it so that the columns sum to 1, essentially what you would do?
Well, no, I mean, I didn't tell you how to do it yet. So one way of how to do it that uses techniques we've seen so far, and this is written in the book if you want, but like the Voronoi diagram looks like this, and it would assign 5 entirely to cluster 1. Okay. There's some way called natural neighbor interpolation, where I can, to assign the weights of here, I pretend that 5 is another center. So now I have 3 centers, and now I create a new Voronoi diagram that looks like this. And now I look at the cell. Okay, so I create these new Voronoi diagrams with respect to this point 5. And then I look at the cell that is associated with 5, and I look at the old Voronoi diagram and the fraction of it that's assigned to, that's in the cell of 1 versus the fraction of it in the cell of 2. That's how I get this proportion. That's one way of doing it. We're going to look at a more kind of statistical view of probability view of how to assign these weights. But this is kind of a discrete geometric view. Right, so it's a little bit more complicated. How do you assign these weights? It's not entirely clear just by looking at this instance. And this makes sense when you have lots more centers, for instance. So it's used for like interpolating, like I have a bunch of data on a map, and then I have, I only have values at certain of the points, and then I have a new point I want to estimate the value, I want to interpolate from the values of its neighbors, and so then I would do something like this. That's more where this is. But that's one way of doing it. We're going to use, look at a probabilistic view of this. Okay. So let's say mixture of Gaussians. Okay, and we're going to build this up. And okay, so what we're going to, in order to do this, we're going to say our goal is to fit some data x in our D with k Gaussians. Okay, and by fit, I want to maximize the joint likelihood. I'll assume x is IID, so it's the product of the individual likelihoods. Okay, so I need to define the likelihood of one Gaussian. And if you remember, Gaussian likelihood is going to be a function, and I'm going to have two parameters, mu and sigma, and I'll explain what these are, of a point x. Okay, and this is going to be, I'll leave a spot here. Remember, it's this e to some function. It's e to the minus 1/2 x minus mu, the inverse of sigma x minus. Okay, and then there's going to be some constant out in front here. I'll write this down in a second. Okay, so what is this? How do I look at this? I'm going to have mu is going to be a point in our D, and sigma is going to be a matrix in R D by D. This is going to be the covariance matrix. Okay, so if you remember, we had written up a Gaussian before in a form that looked like, we had written this up before at x, which was e to the minus x minus mu by squared to sigma squared, something like this, where this was some notion of the standard deviation squares the variance, and it was the distance squared here from the mean. Okay, this one is a little bit more complex, and it turns out it will be easy to deal with. That's why I'm going to write it out. But this is going to be a matrix, a d by d matrix. Yeah.
That's the first power, x minus mu to the...
This is minus 1/2.
Sorry, minus 1/2 times x minus mu to what?
This is t transpose.
Oh, transpose.
Yeah, transpose. Yeah, so if you remember, this is, I need to write it like this. These are vectors in our D. And if I remember, a V transpose V is equal to the dot product VV, which is equal to the norm of V squared. Okay, so this, if I ignore this matrix in front here, and this minus 1/2 is the minus 1/2, that's insane here, and this x minus mu is a vector, and that transpose is actually just the dot product, and the dot product of the vector with itself is just the norm squared of that vector. But if that vector is the distance, the Euclidean distance between x and mu, then this is the distance squared. Okay, so this part, right? So this is basically the distance squared. So when v equals x minus mu, then this goes to x minus mu squared, which is familiar from up here. Okay, so that's what's going on here. But there's this kind of weird, there's this matrix, and I've inverted it, that's going on in the middle. What this is doing is this is creating what's called a Mahalanobis so distance. Okay, so this is what I've done is I've written some sort of stretched distance. This is a kind of a warped version of Euclidean distance. Okay, and so what's going on here is that if I have two points, x and mu, with Euclidean distance, this is Euclidean distance is just the straight line distance. All the points at a certain distance are lie on this ball. With the Mahalanobis distance, what happens instead is that it's going to get this this sort of ellipse instead. This would be the Mahalanobis. Okay, so this is the Mahalanobis. It's defined by some sort of ellipse. It's an ellipse, so it's still kind of like a ball, but it's just the space has been stretched or warped in some way, so the distances are different along different directions.
If sigma is an identity matrix, is it just a ball?
Yes, great, good. So sigma describes the amount of warping and the direction of warping. And if this is the identity matrix, then I'm going to get back exactly the blue ball. A circle is a special case of the ellipse where there's like no stretching. Okay, so if I put the identity matrix in here, then this is going to have no stretching, and it's going to be the Euclidean distance. But what this allows me to do is to say, well, I want to stretch this a little bit, and the idea is that there's some Gaussian distribution, but it's not totally symmetric. Right? So if I have data points that look more kind of like this. Okay, if the data points looks like this, then I can pick some mean here, and then I want to define some basis using PCA, in fact. Right, so PCA gives me some principal components that fit here, and these correspond with this ellipse that goes around here. Okay, so now I want to say a new data point, how well does it fit inside of this, how well does it fit by this function? I don't just look at the distance, I look at the Mahalanobis distance depending on how I fit my data. And so this one's actually not so bad because even though it's long in this direction, that's the direction the data varies upon. So I want to be able to capture with my Gaussians that the data can have this stretch factor. Okay? If I restrict the stretch factor to be along the coordinate axes, right? So the ellipse has to kind of be orthogonal along the coordinate axes, then this matrix is only going to have stuff on just the diagonals. But if I allow it to be rotated, then it can be like this. Then it can be It could be entries everywhere. Okay, and so think of how PCA is capturing kind of the subspace here. That's kind of the right way to think about this. Turns out we won't need to do PCA inside of the algorithm we're going to do, but there are kind of other algorithms with stronger guarantees, and they need to do PCA as one of the steps inside. And they filter out noise and use that for other sort of stuff. Okay, so that's kind of how to interpret this. We're going to not just choose the center of our cluster, mu, the center, but we're also going to choose this kind of stretch factor of how to fit it. And this will be built into this mixture of Gaussians algorithm. And it's just going to be a simple extension of Lloyd's algorithm here. Okay, one more thing I left out up here, which was this constant c. I want this to be a probability density function. So now let me write what's going to go in here. And this is going to be 2 pi to the power d over, so 1 over 2 pi to the power d over 2. And 1 over the square root of the determinant of sigma. The determinant, it looks kind of like a norm. Again, it's a scale quantity. The determinant only has single bars. If you haven't heard what the determinant is anymore, I'm not going to explain it, but it's some scale quantity for this matrix. Okay. Yeah, computing the determinant of a big matrix efficiently is like a long kind of how fast of an algorithm can you design for that is kind of this kind of old algorithms question. And it's like it's defined recursively, and it's okay. But if you put this coefficient in front, then you integrate over this, it's going to be 1. Okay, so technically we might want to use this. I don't think we don't actually need that, but it's there. Okay, so now our goal. So now our goal is going to be to find F1, F2 up to Fk. That's going to maximize the so this is a product over max of Fi. Let's call this set. So max Fi in the set of f of I of x. Okay? So for every point, I'm basically going to assign it to the Gaussian. This is the stretch Gaussian, which maximizes the likelihood function. Likelihood function of that form. Right? So technically, I'll have a mu I and a sigma I, and this will be f of I. Okay, so I want to find the set of these Gaussian functions so that for the data set X, I'm maximizing the product over all the points assigned to the maximum, the cluster which maximizes this. Okay, and so this is equivalent to minimize instead the sum of the, I think I want to put the negative, oh yeah, minimum of the negative of the log of f of x. Okay, so So it's equivalent to minimizing where I took a negative and I took a log, right? So the same solution that maximizes this will also minimize this cost function, right? And this is nicer because now we have a sum. Sums are a little bit easier to deal with than products. And I've taken a log, and actually let's write it as the natural log. And now ignoring constants, this is going to be minimize of the min of let's see, of mu I sigma I squared of the right, of just this. Okay? So this part, assuming that the sigma does not, they're all scaled the same, then I can drop this whole term. This is a constant, this is a constant. The log, this log takes care of the exponent. Those cancel each other out. I have a minus sign here that takes care of the minus sign inside there, and the 1/2 I can ignore, and I get this term left over. And this is actually the distance squared where I have this Mahalanobis distance, where I've defined this weird norm, this stretch norm. Okay, so it's now minimizing the sum of squared distances under this stretch norm. Okay, and so if this is identity, then this is exactly the k-means formulation. Right, so if sigma equals the identity, then this is exactly k-means. Okay, so we've actually derived the k-means formulation, which is cool. Okay, so so that's why it's squared distances. Okay, good. So this makes sense. So we're going to solve this formulation, which is kind of this fancier version of k-means, and we're going to do a soft clustering formulation of it because they're probably distributions, so they might overlap. So I might not know which distribution it comes from, and that'll end up being a bit ends up being more stable, and there's nice properties about it. Okay, so we'll see if I write on this part of the board. Oh, question.
Sorry, where it says at the very bottom, where it says x minus the mu I squared, and then the sigma term right there.
Yeah.
What's that sigma represent right there?
Oh, it's this sigma term, which is this scaling effect here. So
I'm confused why it's wrote in like the.
Some shorthand. Sometimes you would write Mahalanobis distance in this way. It's kind of like a norm, but I've changed the norm in some way, so I give it a subscript. I just wanted it to look like k-means. So
I see. Okay.
You might see this notation someplace. You might, you might write this as the distance, Mahalanobis of x squared instead. There are other ways you can give this, but I want to make clear that this quantity here is a distance, right? I kind of derived it. I erased my derivation of it. Oh no, it's here, right? So yeah, so I mean this this gives me a distance here, and then this is just some stretching of the distance. So I'm not going to dive too much into thinking about this right now, but as long as this is a positive definite matrix, it's still a metric distance. It has lots of nice properties.
Okay,
Yeah, it's just notation, so it's clear it looks like a distance.
Okay.
Yeah.
Maybe I missed it, but we need sigma, the Mahomes matrix, to do this.
Yeah.
Where is that coming from?
Yeah, so, okay, so I'm about to write down the algorithm,
Okay.
and it's gonna look like Lloyd's algorithm all the way over there, except instead of step 2, instead of having to calculate just the mean, which will end up being our mu, we're also gonna have to use something to calculate sigma. Turns out it's not very hard. I'll just write it down. But just like the average gives us the right mean, which will be the case here as well, there'll be another kind of averaging step that will give us the right sigma to fit them up. Okay? And so, yeah. If I write the algorithm here, is that going to be readable for everyone? Okay, so, okay, so let's write, so mix of Gaussians, and this will take in a set x and a value k. Okay, and so my step 0 init, again, S is going to be some subset of X, but then I want to do for all X and X, I want to assign a weight. For J equals 1 for phi of S X equal S J and 0 0 otherwise. Okay, so I'm going to first assign a weight. We're going to do a weighted soft clustering here, and I'll explain it in here, and then you'll see it's not going to be much harder to do. It'll require one extra step. But I'm going to assign weights for all the points here. And so first I've assigned it just in kind of the, every point gets a weight of 1 for the closest point and 0 otherwise. Okay? And then I'm going to repeat, and then within this for J equals 1 to K. Now I'm going to do the step where I am, it's a little bit easier to write here. I've done the assignment step first, so now I'm going to start with step 2 over there inside of this for all K. So I'm going to first, so this will be 2A is going to be calculate the total weight Okay, so I'm going to calculate the total weight assigned to cluster J. This would just be the number of points, but I'll need this to like properly normalize averages. So I'm going to take weighted averages. Okay, so mu J, right, the new center is going to be 1 over the total weight times the sum of weight J of X times X. Okay, so this is a weighted average. So this is the total weight. This is a weighted average. Right, so I'm doing a weighted average now. So now, if a point gets a weight of 1, it counts towards 1. If it gets a weight of 1/2, how much I count that for the center is only proportional to its weight. Okay? And then for C, and now I need to calculate sigma J And it turns out this is also easy. It's going to be a weighted average. And it's going to have a component from each of the data points, x, times the weight of that data point, times x minus mu j, x minus mu j transpose. Okay, so this is now an outer product. Okay, so this is an outer product. This says how much is this point worth, and then given the mean, this is a vector that points in the direction from the mean to x. Right? So this is mu j, and this is x up here, and this is this vector, and I've weighted the vector. If it's all the way in, it gets a weight of 1. If it's halfway in, it gets a weight of 1/2. Right? And this is an outer product of the vector. Remember, I'm doing something like, and this will be something like an Eigen Decomposition. You can think of it in terms of the Eigen Decomposition of the data. And so remember, the Eigen Decomposition is, I can think of that as A transpose. Right? And this is a rank 1A times a rank 1 A transpose. And it gives me one D by D matrix, so it's going to be rank 1. And I'm going to add all D of these together. Right, so I'm basically, and the mu has done the centering step for me of PCA. So I found mu, so I've done the centering step. I just build that into this calculation, and I'm computing these kind of directional elements, and I just add them up into this D by D matrix. And implicitly, the eigenvalues of this are the right singular vectors or the principal components of the data. But I don't need to actually calculate them. I just need this matrix sigma. Okay, so that's step 2. And now step 3, which was step 1. So for all x in x, I need to do this one thing. For all j in 1 to k, I'm going to set the weight of j of x. So this is the assignment step, but now it's with weights. Is going to be f of j of x divided by the sum over j of j prime of x. Okay, so I've done this L1 normalization built in here, but the weight is just this f of j matrix, where f of j of x is equal to f of mu j sigma j of x. So I calculated mu j and sigma j, and those go kind of into here. And again, I'm just iterating between these two steps. I recalculate kind of the best fitting Gaussian, which is 3 steps. I get the total weight, I calculate the weighted average, I calculate the weighted covariance. Right? That gives me the model for the Gaussian. And then once I've done this for all the Gaussian functions, I create the normalized weights. Okay, so this. Okay, if I had put this up like on the first day of class, you guys would probably just be like, your eyes would be rolling in the back of your head or something. But I hope now this is actually kind of something you can understand. It should be pretty straightforward once we've gone through this. Yeah.
I think you may need j for the big X, like X in X. The sum, the unsubscribed of the sigma or sum. Like for A, Wj equal to sum X in X, right? the next big X.
Yeah, so in the notes I used I for this subscript and carried them all the way through. I hope, but I like to have x's be indexed by I, so I swapped it on the fly. But I hope that's okay. Is that the question? I don't index the x's. I don't need to
You
index.
need to index the next X, the big X, not the small. During the
No,
step 2.
X is fixed. This big X is fixed. This is my input data, it's fixed. So this is fixed, and I'm just fitting a different set of clusters that look like this on top of it every time. This is my function f of j equals f of, but x is fixed here. This is one x, there might be another x that's up here that's shaped in a different way. Each cluster can be shaped in a way that's different.
You use the weight to control which clustering each point should be.
Yes,
Okay.
yeah, the weight controls it. I don't explicitly assign it, but you know, if one cluster looks like this and this is another one, these points will be close to 1. These will be really close to 1 for this one, and really 0 for this other cluster over here. Okay, and then there's like you do this until there's some stopping condition. It's not combinatorial anymore. It's kind of a continuous search of these parameter space. So you might want to look at that, the cost function. The cost function from here is the change is becoming small.
On step 1, we have phi sub s of x is sj, meaning that's the closest one that, or the closest point that, sorry,
Yeah.
the closest point to x, right, from s.
So assign x's to closest sj and s.
Right. And later, we're switching mu and sigma. Is mu analogous to s sub j, or are they the same?
Yeah. Yeah. So those. Right. So I just used this for initialization. You're right. I probably should have tried to use the same thing here. Let's swap this. Let's say that M is going to be a set of mu1, mu2, up to mu k. And initially, these will be a subset of x. And this will be mu phi m. Yeah. Does that make sense?
Yeah.
Yeah, even if I had done this, these get kind of thrown away after I get into the loop. I just need to get the weights initialized. The weights serve as kind of a soft version of this phi function, right? They kind of they don't enforce it binary or kind of combinatorial. They allow it to be soft. But to initialize it, I need to somehow pick some weights, and I'll initialize it probably with k-means plus plus, or the same way I would do with the k-means. Follow up, right?
Okay. Also, with like the transpose and the outer product and stuff, it's hard to imagine conceptually. Is this process like the continuous version of k-means, or is it different?
So there are two ways you can think of it as being continuous. One is with the weights. The weights mean that it's no longer exactly in one class, and maybe that means continuous. And the other is I allow the distance to be a Mahalanobis distance to stretch, and I'm kind of learning that. But the centers, the UJs plays exactly the same role as the centers. That has not changed. And in fact, those were continuous before anyways. So it's still kind of continuous, but I no longer have this fixed Voronoi diagram deciding the assignment. It's now decided by these likelihood functions, which I'm calculating kind of, and then I'm weighting based on those.
I'm still kind of wondering how this outer product provides us the proper like matrix to define that ellipse in the right
Yep.
way. Like,
Right.
I guess what does the outer product represent?
Okay, so good. So let's look at this again. I drew like there's some, if I took some mu and x here, then this vector, right? The vector from mu j right? The vector from mu j to x is x minus mu j. That's a vector. Okay? If I do an outer product of this vector with itself, I'm going to get a d by d matrix. Okay? If I just let me write this is use a little bit more space here, so let me write over here. So let's say I have a matrix that's A, okay, which is going to be A1, A2, up to AN, and AI is going to correspond with weight of, and this will be matrix AJ for the J thing, right? Weight of J of xi times, or let's say square root of this, x minus mu of J. Okay, so I take all these vectors, each one is this picture here, from mu of j to x. And it's been weighted by how much I trust x to be a factor of here, okay? I take all these and I create a matrix. This is R of n by d. This is an n by d matrix. Sigma j is then just going to be AJ transpose. Okay? It turns out that this is equivalent to I equals 1 to n AJ transpose. And this is equal to I equals 1 to n of, this is a scalar, so I factor both terms out, so the square root goes away, times x minus mu j, x minus mu j transpose, which is what I wrote over here. I've normalized by the total weight. So ignoring it, but okay, and that forces that this term stays a constant by normalizing by the total weight. Otherwise, I don't get some distribution that just have a higher value, and that kind of throws off the total weight. Okay, but that's how I get this term here. So if you understand the connection between the SVD and the eigenvalues, then you can derive this.
I might be a little confused here, but are the weights just the amount of, like, kind of like how much they belong to each cluster? Is that what the
Yeah, correct.
Oh, okay.
Yeah. The weight is how much it belongs to a cluster. If it's 1, it completely belongs. If it's 0.6, it's kind of 60% belong and 40% elsewhere. And I've now that I've defined this probabilistically using kind of likelihoods of Gaussians, I can just compare directly the likelihoods. Right? I can say it's the likelihood of this Gaussian is kind of is 150% of this other Gaussian. So I get 0.6 and 0.4. right? And that's how I set my weights.
Okay, okay.
And that's what this step is doing, right? This is the total, the sum of the likelihoods, and this is the likelihood of this particular cluster.
And then, so the whole point of this algorithm, the mix of Gaussians, is just to assign those weights to each data point, basically. The amount it belongs to which clusters.
Yeah, right. That's
Okay.
right. Yeah. So it turns out, like, I could have written this up without the weights. That's kind of turned out to be much less stable, and this one becomes much more likely to give you a better answer, and it's not that much harder. There's some more notation you have to do with the weights, but this is the right way to solve this problem.
Okay.
Yeah, the other one will not necessarily converge to the right answer. You get these weird issues on when two clusters overlap, you falsely split them, and depending on where it overlaps, you get some weird stuff that happens. So, like, imagine if I had another cluster that went like this. Okay, what's going to happen is there's going to be a dividing line, and the red cluster, it's not going to affect too much. But for the purple cluster, I'm only going to get stuff inside of here. And that's going to cause this mean to end up being shifted in a way that's kind of incorrect. Whereas if it really was two overlapping distributions, then the weighted formulation will actually converge to the overlapping distributions. Where the one that's not weighted will try and force the distributions not to be overlapping. And the weights will just handle this naturally. And so in practice, they overlap a little bit, and if they overlap like this, then it would be a problem with that. But this is the simple solution. And I hope you guys were also ready for it. So I think so. I saw some grimacing there in the back. No, okay. So you know, like I took Lloyd's step. And I did Lloyd's algorithm, and I only changed two things to Lloyd's algorithm. One, I calculated this covariance function. This covariance step, as we know from PCA, is pretty simple. I just add up these outer products. Okay, so that's something you can do. And these outer products then gives you this F function, this likelihood function. And these likelihood functions give you a very natural way of assigning these weights. So it doesn't have to be just based on the Voronoi diagram. Okay? And these weights are just, I evaluate this function at every point x. And so probably I should write this a little better. I evaluate it at all functions, and then the weight, so I only have to calculate the sum once. But, the way I've written, I've got an extra factor j in the runtime. Okay. But it's a pretty natural way of assigning these weights, just following this formula. And so instead of this kind of the assignment be determined by the Voronoi diagram, I've defined it by these in a soft way from these weights. Okay, so.
Sorry, the mu j as well, it's just the two equivalent ways of thinking about it are both the center of a particular Gaussian, but also the center, in more like Voronoi, like Sykes way of thinking about it.
Yeah.
Function in both capacities fully, right?
Yeah. 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 So those play the exact same role in both formulations, but the assignment is soft here. Yeah.
So when would we want to use the soft clustering versus the harder clustering?
So if you're doing mixture of Gaussians, I would use the soft clustering because one, there's a natural way of defining weights here, and two, it handles this issue with the overlapping distributions in a way that is correct. If you're using kind of just regular k-means formulation with Lloyd's algorithm, I would do the hard clustering.
So that'd be more for if we knew we had clusters that didn't overlap.
It's more of kind of if you don't necessarily know that there are actually Gaussians, and you just want to run a quick and dirty clustering for visualization or for understanding, kind of the first thing you should try is Lloyd's algorithm for k-means clustering. That would just be the first thing I would try. And if you have, you need Euclidean distance for both of them, right? If you don't have Euclidean distance, then you can't use either of these. But if you're more confident about kind of that you think it's arising from different centers with Gaussian noise, then go ahead and use Mixture of Gaussians. If you'd like more explanation or you'd like to be able to speak probabilistically, then this gives you a little bit extra. There's some extra overhead in running it, but if that's not an issue, then this will probably give you a more stable result. In case there's actually some generative model from the data and they overlap, this will handle it fine. The k-means formulation will not. This one can also handle clusters which are kind of not, the k-means essentially assumes the clusters are round. This one does not assume they're round. They could be kind of these ellipse formulations. Yeah.
When would we have a Euclidean distance?
When would you not have Euclidean distance?
Yeah.
Okay, so I think one of the best examples is kind of what we worked through the first few weeks in the DataMine class is that where people often model these documents with words on them as these sets of words that they contain, and then they measure the distance between the sets as so as the Jacquard distance. Okay, so it's not just that you don't have Euclidean distance, you don't even have vectors. I just have sets. I want to measure distance between two sets. I can't do something like a mean. I can't draw a straight line between two sets. But there are these really nice distances that work well and model the data pretty well. So that's one example. Also things where if you're probability distributions, you can represent them as vectors, but then you want to work on this information manifold and use something like Hellinger distance or Jensen-Shannon or Mikhail divergence. And those also aren't Euclidean. You can kind of force something like this onto that, but that's hard. And then, you can, chapter 4 in the book is all about distances. So you've got some stuff to glance at. One thing I did, we're going to start on classification on Wednesday. This is it for clustering. I kind of talked about a fairly limited class of clusterings. I thought about talking, we didn't quite have time for the mean shift algorithm, or there's also hierarchical clustering and density-based clustering. These are completely different ways of thinking about dividing your data up into these different subsets. And they work under different formulations, different assumptions. So this is kind of unlike regression and dimensionality reduction, where those really were like 95% of what you would do. This is more like 70% of how you would do clustering. Those kind of the topics we kind of give you a glimpse of it. There's more if you want to just glance through the book, you can get an idea of some of that. Okay, we'll stop here and we'll start on classification on Wednesday.